Hello everyone, I'm Ethan, and we're going to be talking about weak-heaps today. This presentation is going to be moved pretty fast because we have a lot of stuff to cover, so I hope you'll stick with me. So the weak-heap was defined by Dr. Dutton in 1992, and it's useful because it's a heap structure that uses near-optimal comparisons. Right, so to create a weak-heap, we're going to just modify some traditional heap requirements. So we're going to keep the binary tree structure, but our root is going to have no left subtree. Nodes must be greater or less than their right child only, so we're not going to really compare them with their left child or subtree at all. And then nodes of less than two children can be scattered in the bottom two levels instead of just the bottom level in a single section. The weak-heap supports creation, insertion, extract, min-max, and also merge. And if you have a pointer implementation, you can also do decrease key and delete. Our two common implementations are array-based, but for that we're going to need an additional reverse array. It can be an order and array. We'll see that on the next slide. It's more space efficient since we don't need to keep track of pointers, and we're going to be using that implementation in this presentation. But for pointer-based, we can use efficient delete and decrease key since we know the location of those nodes already. The reverse array is a simple bit array of 0, 1 for each node. It's going to allow us to determine the left and right child location for each node, and it's useful for swapping subtrees quickly, order one, nice and easy. So I want to present the concept of a distinguished ancestor to you all. It is the closest ancestor for which a node must fulfill the heap property. So basically we're going to follow ancestors until the right child found, and we can take the parent of that right child. So as you can see here, our node 2 is going to have a distinguished ancestor of node 4, node 1, distinguished ancestor of node 3, node 3, distinguished ancestor of node 4. Nice and easy. To construct a weak max heap, we're going to be using max heaps in this presentation. To construct a weak heap, we're going to begin with a weak heap shape. We're going to create a reverse array, begin with all zeros, and we're going to unmerge the binary tree into two smaller binary trees, and then create a weak max heap on each of those. But that's not quite necessary here since we're using an implicit array implementation. What we're going to do here is we're going to recursively construct weak heaps going bottom up and merge as we go. And it's actually a lot easier than it sounds. So we're going to begin with a weak heap shape here. We're going to merge bottom up, so we're going to start at the last element, compare its distinguished ancestor, and swap if we need to. And we just did right there, right? The 5 and the 7 swapped, and whenever we swap, we're going to reverse the reverse bit for the child, for the lower node on the lower level. Right, we're going to go along 6 and 3, 9, 6 are going to swap, 6 reverse bit gets changed to 1, and we're just going to keep going up. And then as you can see, when you get to 9 and 12, when that reverse bit swaps, we're actually going to reverse the subtrees. That's what the reverse bit does. It keeps track of which subtree is which. And we don't even have to change the array to do that. It's just implicit like that, and that's how we can do an order one time. Exactly n-1 compares for this. It's pretty efficient. To insert into a weak heap, we're going to add a leaf node. We did right there. We added the 8 down there. And what we're basically going to do is just bubble up, right? So the 8 and 2 are going to swap, 7 and 8 are going to swap, 8 and 9 are not going to swap actually, and that's all we're going to do here. Let's try it again, right? So we're going to add an 11 down there, and we want to compare with this distinguished ancestor as we go, instead of just the parent. So we're going to bubble up, try 11 and 12, we can't do that, and that's all. So this is order 1 amortized, but at most the ceiling of log base 2n compares. To extract the max in the weak heap, we're going to get the root value. We're going to replace with the last value in the array since we know that that we'll not have children, we won't have to really deal with any like funny stuff. Replace the last value, and we're going to bubble down, right? So 11, 9 are not going to swap, and that's all there is to it. But let's do another example. Get the root value 11, we're going to swap with the 2 at the bottom, right? And now we want to bubble down. So the 9 and 2 are going to swap, and that's going to change the reverse bit, which swaps the subtrees of that node. We're going to bubble down again, swapping the subtrees, and that's all. So this will also have at most ceiling of log n compares. So now we're going to merge some weak heaps. So the rules for this are that we're going to compare the two root nodes. The larger value node has become the new root, and the smaller value node becomes the right child of the new root. And then the smaller value node's left subtree, which didn't exist before, is going to become the right subtree of the larger value node. So let me show you this. We're going to have two compatible weak heaps. And so for a weak heap to be compatible with each other, basically means that it's going to create a new weak heap. We just need the nodes less than 2 children must be at 1 of 2 consecutive levels. And that makes sense, right? Because all of these nodes right here after the root are going to be at the same level. And so by our weak heap definition, we want those to be at the bottom 2 levels, right? And so we're going to combine those. 9 is greater than 7, so 9's become the new root, 7's become the right child. And then this subtree over here, 9's right subtree, has become 7's left subtree. Perfect, just like that. We're going to combine them, and it's nice and easy. Order one time. Delete and decrease key is efficient only when the node location is known for a pointer implementation, basically. So when you decrease key, we're just going to set that key, we're going to bubble up, and that's going to be order log n, since we're doing at most one comparison each level, as for most of the other stuff, right? For delete, we're going to decrease key to the extreme, we're going to remove the root, and then we're going to have to do our extract root procedure and bubble down backwards. So we're going to bubble up and bubble down for delete. Order log n both ways. Now, what's very special about weak-heaps is that they have a very, very efficient sort mechanism. So we have extremely close to optimal comparisons, right? That's a pretty good worst case. Worst case in sorting indices, you do that in database and stuff like that. It is constant optimal. N log n plus 0.089n has very low additional space, only 1 bit per node, order n. It's empirically quick, even for things like integers, but especially for strings and other things that take complex comparisons. And it's pretty simple to implement. So what we're going to do is we're going to construct a weak heap, remove the root, and merge the resulting weak heap forest. That's all there is to it, right? We begin with an array, create a reverse array, and that's our structure. We're going to weak-heapify this structure, so here's just a 4 and 1 are going to swap, and we're going to move the root to the array end. Now we're going to merge the forest, right? So we're going to compare 3 with its ancestors and merge up as we go. So 3 is going to merge with 2, then the 3-2 structure is going to merge with the 4-1 structure. We're going to create that. The root, I added the root to index 0 for clarity here. The implementation doesn't really do that, but just so that we can see what's happening and why the sort works. We're going to remove the root again. We have the forest again. We're going to merge 1 with 3. That's going to make this structure, right? So 3 becomes the new root, 1 becomes the right child, and 2 is moved over. Perfect, just like that. The root added to index 0 for clarity again here. And as you can see, as we go along, we're putting the root at the end of the array. So as we go along, we're just sorting less and less, and that top node is going to be moved to the end of the array, right? So here's our resulting forest. We're going to do it once more, merge those two, and a resulting forest after that is only 1 node, but it's already in place. So now we have a sorted array stored in indices 1 through n. Here's just the implementation of the algorithms, right? Odd just returns odd, swap's a simple swap. Distinguished parent is going to go up left nodes until it hits up left child's until it hits a right child, and it's going to take the parent. Merge, we're going to check if those nodes need to swap, then they're going to swap, and the reverse will just not the reverse, as we saw before. Weak-Heapify, we're just going to merge up as we go with distinguished parent. We saw that when we first did this. We're going to take the last item, find distinguished parent, merge them, and then we're going to keep going along until we hit the top. For merge forest, you can see the algorithm here. It's a little bit complicated, but basically we're going to take the forest at the end, or the tree at the end, and we're going to compare it as it goes up its ancestors, and we're going to merge as it goes along, is the gist of it. For weak-heap sort, we saw before, we're going to weak-heapify, remove the root, and then we're going to merge forest. Right, and here it is in C. I implemented this just to make sure everything worked as I thought it would. You can see I did GCC, I got 1, 2, 3, 4, 9, and that's all. So to recap for weak-heaps, weak-heaps are a very efficient heap structure with near optimal comparisons, which makes it very useful for sorting, and they're also very simple to define. Thank you for listening to my presentation. That's all. Have a great day.